All right, let's look a little bit carefully at how we add electric fields. What we've got to remember is that electric fields, just like forces, are vectors. So electric fields add as vectors. I could be fancy and say superpose, but I will say add as vectors. Now, we don't want to drag you through a bunch of formal vector notation, etc., so we're going to keep it 1D. You can still appreciate the directional aspects of vectors even just in 1D. So let's lay down an axis here, plus x, x-axis, and we're going to put 4 charges on it. All right, 4, and 2, and 3, and 4. And I'm going to be very unimaginative and call their positions A, B, C, and D. And I'm going to be further unimaginative and give them charges of 1 microcoulomb, 2 microcoulombs, 3 microcoulombs, and 4 microcoulombs. There we go. Okay. What we want to do is say, let's see, is figure out the field at point C. What field is the 3 microcoulomb charge experiencing? So what is the E field at point C? Okay. Well, I'd probably write this something like this. The E field at point C is equal to the field created by each charge. So it's the E field of A at point C, which you could use a notation maybe something like this. E of A dash C means the charge at point A at the point C, plus the E field of B at point C, plus the E field of D at point C. Now which one is missing? We didn't do the field of C at point C. Okay? So when you're thinking about the field somewhere, if there's a charge on that point, you don't count that charge. It would be infinity, right? If there's a point charge and it's right there and we said R equals 0, it would be an infinitely large field there. We don't do that. At point C, the charge is experiencing that field. It doesn't contribute to that field. All right? So that's why I just did A, B, and D. And I wrote them as vectors, put vector hats on them to remind us that we have to think about the direction. So if we now look down and we're just going to start plotting the vectors, A at point C, what is that going to be? Let's see. So E at C, let's see. It's going to be KE times 1 microcoulomb, and let's make the spacing of all these 1 meter just to make the numbers easy. So they're all 1 meter apart. And so that's going to be KE times the charge, 1 microcoulomb, 10 to the minus 6, over the separation squared, 1 squared. Is what that's going to give you. So that's 9 times 10 to the 9 for KE. And let's see. Except that's not right. It's 2 meters from point C. Right? So 2 squared, sorry. Over 2 squared. Now I made it positive. Why did I make it positive? Because this is a positive charge. It's creating a field, and it's going to be this way. Right? If we imagine a positive test charge here, it'd be repelled by this positive charge, just like the 3 microcoulombs. It'd be that direction. And that is the positive x direction. So that's why I made that positive. This one is 2 microcoulombs, and it's 1 meter away. So E beta C would be KE 2 times 10 to the minus 6, and it's 1 meter away, so 1 squared. And then finally, this one is 4 microcoulombs away, or 4 microcoulombs and 1 meter away. So it's KE 4 times 10 to the minus 6, and it's 1 meter away squared again. But this one makes a field this way because it's positive, and if you had a positive test charge here, it'll be pushed that way. It's the opposite of these two because it's on the other side. So the field directions don't follow Cartesian coordinates, they follow spherical coordinates. So if you go on the other side, the R vector points out the other way. So if we had to draw them in space, this one would be the smallest because it's 1 microcoulomb, it's furthest away. That would be E of A on point C, and then B is a lot bigger, twice as much charge, twice as close, 4 times bigger. And then this one is 4 times, twice as big as that one, twice the charge, same distance, but it's the other way. something like that. So if you think of these as vectors and add them up, you're going to see this one's going to win, right? Now let's see if the numbers worked out, because this one is negative. What do we end up with? We end up with KE times 10 to the minus 6, but we have 2 plus 1 is 3 times 10 to the minus 6. Oh, but this is over 4, so we have a fourth here, and we have 2 here, and we have minus 4 here. So, oh, I worked it out. I don't want to do the fraction in my head. We get 7/4. 7/4 times 10 to the minus 6th. And we did that 9 times 10 to the 9, we get the answer in newtons per coulomb. But it comes out negative, because the biggest contributor here, that's bigger than these two, is negative. So this is a case where in one dimension we thought about the vector directions to make sure we actually get the right value. Once we have the field here in newtons per coulomb, if you wanted to know the force on this charge, you would just multiply that newtons per coulomb times 3 times 10 to the minus 6 coulombs, and you get the force, and it'd be this way.